This is lecture 2. So we will continue with geometry of high dimensions. That's what we are going to do for the first 2 weeks. I'm going to recap in one slide before I start. Right? This is what we did already last time. If you have questions on this, you can ask me. Otherwise, we'll start doing new stuff after this slide. So we I didn't give you many examples, but I just told you that in a lot of situations, data points or just vectors in RD, real space, d-dimensional real space, right? Each component is a real number, positive or negative. And viewing them as vectors is useful. It's not just a bookkeeping device to keep a list of things, right? List of components. Again, that's not something that we will delve into in examples, but that's something I told you last time. For what our main focus is to see that for a large number of dimensions, which is the case for a lot of applications, data is, if you had documents, we saw the example of documents being put down as vectors. There are as many components as there are words in the language, and also web pages, right? The web being described as a matrix, and then there are as many components as there are web pages in the billions. So D is very large. Things behave differently. That was our starting point, and we wanted to see some important differences. So one of them was that I told you, and we'll prove that today, that the volume of this hypersphere, I keep in exchanging these two terms, but they mean the same thing. The unit ball, hypersphere, all mean the same thing. Is a set of x in RD such that the length of x is less than or equal to 1. And in the slides, vectors will be boldface. Right here, I can't do that, but and I'll try to do that. Keep the convention that vectors are boldface and scalars are not boldface, right? I mean, but not on the board. Okay, we'll see that. We'll also this other fact, we saw this already. So since the recap, just mentioning it, most of the volume of any d-dimensional object is near the surface, not just for spheres, but for everything. We proved already. And there was no big deal in the proof, except just this sort of calculus thing that you divided the object into tiny infinitesimal cubes and integrated, right? And if you scale a cube down by 1 minus epsilon factor, then you scale the side down by that factor. It's still a cube. That's worth checking. And furthermore, the volume, because it's d-dimensional, just gets scaled by this. So that's a lot of severe scaling in some sense, because d is large. This is the dth power, right? So if you go to 0.9, epsilon is 0.1, this is 0.9, you get 0.9 to the d, which is very small, exponentially small. Okay, that's why the volume is mostly near the surface. So we saw these two things. Now I'm going to start proving some of the other statements that we didn't prove. So I'll prove today first. We'll prove a bunch of things, that the volume of the d-dimensional unit ball, we'll find it. We'll actually more than prove that it goes to 0. We'll actually find it. So it is this integral, right? I mean, so I'm writing down the integral. So that's a little bit of an odd notation because it's d of x1, x2, and so on, because we have d dimensions, d of xd. Bear with that. So, of course, x1 goes from -1 to +1, and x2 goes, once I fix x1 and x2 squared can be at most 1 minus x1 squared, because we are inside the unit sphere. So these are the limits. This is the integral. And yesterday I said try integrating it, and I hope you did, right? I mean, I don't know how many of you did, but you get sine to various powers, right? Sine and cosine to dth powers or more if you did it. But if you did it, you spent that sort of in vain, because we are going to do something better. Just to sort of give you a feel for why it was, multidimensional integral is a bit of a hassle, right? So instead, we'll go to polar coordinates, standard thing that we do in 3 dimensions. And I'm going to draw a little picture on the board. Now, in polar coordinates, I'm going to write this down. This seems completely obvious, except I'm going to try to impress upon you that this is not completely automatic in all cases, so you have to be a little more careful. But let's draw that picture, right? In 2 dimensions or 3 dimensions, 2D is all we can draw. The picture is this, right? So I guess I said, what is d omega? D omega is this infinitesimal surface element. Okay. And r is the radius, polar coordinates, right? So r is the radius. I'm integrating from r equals 0 to 1 because the whole ball of the radius 1. So at the particular r, and this is dr. Okay, so we want to take this infinitesimal area, surface area. Surface area really is a d minus 1 dimensional volume, right? If this was a 2D, if we're really doing it in 2D, it's the length of the curve. If we're doing it in 3D, it's the area of the surface. If you're doing it in 4D, it's the 3-dimensional volume of this, and so on. Okay. So if you're doing it in 10D, this is a 9-dimensional object, right? So this is that scaled by r, right? Just scaled by r. R is less than 1 in this case. Therefore, scaling by r, a d minus 1 dimensional object scales volume by that much, right? So that's the area of that. Okay, and I'm multiplying by dr to get this infinitesimal volume. Okay, so this is times dr. Okay. Is there anything I have to be a little careful about in doing that, or is that completely automatic? Is it all sort of true that, I mean, it's true, but okay, so let me ask you this question. Instead, suppose I had a square in 2 dimensions, and I did the same thing, right? This is the cube. This is r equals 1, and this is radial. So here is another. This is r. This is r equals 1. This is d omega again, and this is it still d omega times r to the d minus 1? I'm sitting in d space. So first question, is the infinitesimal element r to the d minus 1 times d omega? It is, actually. That's not a problem. Is it true that, think about this, is it true that this is equal to r to the d minus 1 d omega dr? Okay, I won't give you the answer, but assume that that is true. Do an integral, you get the wrong area for the square, even in 2D, so you know it's wrong. Okay? These are the same picture, more or less. That is wrong, and this is correct. Why is that? Right. But no, it's okay. Yeah, so the dr, okay, so yeah. What's the reason this is true? The dr here is orthogonal to the surface. Not so there, right? So in 2 and 3 dimensions, we are familiar with this. But in d dimensions, the volume of this would be equal to this times that, provided they're orthogonal. You must take only the height, right? You must take the height just as you do in 2 to 3 dimensions. So d-dimensional volume of an infinitesimal volume is infinitesimal surface area, correct, times height, but the perpendicular height. It cannot be an angular height. Okay? So as I said, you get the wrong answer if you do this and integrate even in 2D. You won't get the right answer. So I'll come back to this point once more, because in 2 and 3D we are familiar with this, right? But in higher dimensions, it may look all right, but it's not all right. Here they are perpendicular. The radial direction is, in fact, orthogonal to the tangential direction, right? So even though, so this is a d minus 1 dimension. Okay, maybe in 3D, this is a 2-dimensional surface, right? There's only one normal, 1-dimensional normal vector space, right? And that's just orthogonal, radial direction. So that's why that's correct for the sphere, but not necessarily always. Okay, good. So for the ball, it's true. These don't interact, so I can move the integrals around. So I get r to the d minus 1 dr. D omega comes out. This integrates to 1 over d, of course, and d omega integrates to a of d, where a of d is the surface area of the d minus 1 dimensional unit ball. So it's a it's a d dimensional unit ball. The surface is d minus 1 dimensional. Okay? So all we have done is related volume to surface area. Okay? So what we have done, maybe it's worth writing on the board, is that the volume equals d 1 over d. 1 over d times surface area. And for the cube, that's not true. So this argument fails. That's not true. Okay? But it's worth thinking about one thing. This argument does give something, some relationship between these two. What does it give? Sorry? So does it give you anything about volume and surface area? Sorry? Less than. Correct. Yeah. It does tell you that volume is at most surface area divided by d, and that's true for the cube. So, I mean, so you know that for the square, right, if the side is 2, the perimeter is 8, the area is 2 squared is 4, dimension is 2, they're equal. But if you go to 3 dimensions, that's not true. So you see that it's less than or equal. But it's always less than or equal to. Why is that? Well, less than or equal to is correct, but why is that true? Sorry? The height cannot be more than the actual dr, right? Dr is the the height is a projection of that. So this is dr height, and then the height is that. It's dr is the hypotenuse of the triangle, so the height is not at most that. So it's true that volume is at most 1 over d times surface area. Okay, so the sphere is exactly equal, but I'm now still left with the problem of computing the surface area, and that's what I'm going to do. Okay, again, if you did this multiple integration, you see that that's much more complicated. We'll do it with a very nice trick, and this trick. I see. I didn't put. Okay. So this is a relation between the sphere and Gaussians, and there are lots of relationships. We are going to see once more. The Gaussian comes in very naturally. So you all, I presume you all know what the Gaussian density is, right? In 1D, it's just e to the minus x squared over 2 if its standard deviation is 1. I've forgotten the 2 here because I don't care about the standard deviation. And I've omitted the normalizing constant. So I'm just going to consider this integral, where the limits are plus to minus infinity, or minus infinity to plus infinity. So the limits are simple, so the integrand can be factored. So you get this, and this is root pi. So if you downloaded the book, there's a proof that this integral is root pi. I guess I won't do that. It's just a definite integral. For instance, if you want to compute the normalizing constant for the Gaussian, that's the integral you want, right? So you get that I of d is this. So in the appendix of our book, we have a proof of that standard thing. I said do on the board, but maybe not. Okay. Now, I'm going to write this I of d now polar coordinates. Okay, and it's okay. So again, it's worth going to that picture. Okay. So now instead of I'm trying to integrate e to the minus length of x squared. Okay, so that quantity here is e to the minus r squared, and you still have r to the d minus 1. Okay. The value of the function is e to the minus r squared. The area is r to the d minus 1 d omega dr. Again, we've removed the d omega, and then I have to do this integral. Okay. This is a moment of this integral you need to do if you want to compute the d minus 1th moment of the Gaussian, right? So that's what that is doing, and you do that Okay. So I'm going to go over not all the details, but I'll tell you some of the substitutions just to get this right. So we put, it's a gamma function basically. So you put r squared equals t. You substitute r squared equals t, and you will get that, provided I didn't make a mistake. So you get this integral. This is what's called the gamma function. It's gamma of d over 2. I guess I did not say that here. Gamma is related, as you know, to the factorial function, right? Gamma of n plus 1 is n factorial. But gamma is defined for any real value. So it's defined whether or not you have integers. For integers, it's a factorial, but it's defined always by that mechanism, right? So gamma of something here, d over 2 is e to the minus t, that thing minus 1. It's a moment of the exponential probability density, right? E to the minus t is an exponential probability density. It's a moment of that. Okay. So that's a way to compute I of d, but we know that I of d is that from the previous slide, so we equate these two. That gives me A of d, and this gives me V of d. Okay? So that's the volume and surface area of the sphere. So as you see, this is much simpler to do. Once you connect with the Gaussian, then perhaps we did by just multiple integration. Now the thing to observe from this is gamma of d, I didn't say that on the slide, but gamma of d over 2, okay, is less than or equal to c to the d to the d over 2. It's like the factorial function. It's like the factorial function. So n factorial, you know, is n to the n over e to the n approximately. There's a root n, but I think root n is upstairs. This is Stirling's approximation. So that is going to lead us, okay, before I go on, okay, I see I did draw that picture here. That's just the same picture as that, handwritten, but I stress the point that the 90 degrees is important. So the dr and surface area is perpendicular. I've already said that, but we want to be careful that that's true before we claim that that is the volume. Okay. Now, so that proof is finished, and I'm going to have 4 or 5 observations about the proof before I go on to the next theorem. The first worry or question is the following. D-dimensional unit sphere is just, if I take a d plus 1 dimensional sphere, cut it in the middle, I get a d-dimensional sphere. So a d-dimensional sphere is a subset of the d minus 1 dimensional sphere. It's just the equatorial plane if you want. So that would seem to say that the volumes should be in that order, right? We know that's not true, even in 3 dimensions. In 3 dimensions, unit ball has volume 4/3, right? Maybe it's true in 3 dimensions. I might be wrong. 4/3 pi r cubed, 4/3 pi, right? For the volume, and the area of a circle of radius 1 is pi r squared. So the volume is in fact greater than, so okay, I was wrong there. So I think you have to go to 6 dimensions. So V of 6 is not greater than or equal to V of 5. Okay? But 2 and 3 it's true. Okay? So is that, okay, so we know that it's not true ultimately because, as I said, the lemma implies asymptotically V of d is c to the d divided by d to the d over 2. This is the gamma function, right? That was there in the last slide. So this obviously goes to 0. Not only that, if I take V of d over V of d plus 1, pretend, I mean, they are, okay, there is, you have to be a little more careful because it's not a very nice function that the limit exists so simply, but pretend the limit exists. This limit is what? From that formula here. Suppose you believe that, then what's the limit as d goes to infinity of V of d over V of d plus 1? Just c over root d roughly. But it goes to 0, right? This goes to 0. So obviously that's false. Okay. Asymptotically, V of d plus 1 is less than V of d, even though in 2 and 3 dimensions it's not the case. Okay. So why are these two not contradictory statements? So that's worth thinking about for a minute, right? So again, the d-dimensional sphere is a subset of the d plus 1 dimensional, yet its volume seems to be more asymptotically when d is large enough. So is that contradictory or not? It's not contradictory because it's true. Anybody wants to think of a reason that it's not contradictory? Yeah, so because it's comparing apples and oranges, exactly, right? So comparing these two is comparing apples and oranges because in 2 and 3 dimensions, this is square feet, this is cubic feet. So you don't say that 5 square feet is less than or equal to 6 cubic feet, right? So they're different units, they're different quantities. So we don't have, just a sanity check. Now, a little harder question. So in this integration, I used the Gaussian. I pulled it out of the hat, right? So going back 2 slides, I just pulled this I of d out of the hat, right? And then related it. So what I did was I computed I of d 2 ways. One way led me to a formula involving the surface area. Another way led me to a closed form polar coordinates but closed form formula. And I related the two to get the surface area. So I pulled it out of the hat. Now, is there something else you can do besides Gaussian? So Gaussian is e to the minus x squared, length of x squared. This is Euclidean length. So if you will, the 2 norm, right? So could I have used the 1 norm instead? Okay. So I could try to do the integral. I could try to do I prime d is equal to the integral of e to the minus 1 norm of x dx and try to relate that to the surface area. Can I do that? What might go wrong if you try to do that? The continuity, yeah, okay, it's not continuous, but we're integrating, not differentiating, so that may not be a problem. So 2 things happened which are nice for us when we use Gaussians. And it's probably worth noting these properties of the Gaussian. Maybe I should have said that. So here's one thing that happened, right? We were able to split it up into just a product of one-dimensional integrals, which we know how to do. That's fact number 1. What's the other nice thing that happened? Constant, radially symmetric. So we got this. So we also got this where it's a function of just r. That means it's radially symmetric, right? At the same r, that function is the same value. So the Gaussian is the only thing that has both these properties where it's separable, you can split it up, and it's radially symmetric. Right? So I cannot use that. I cannot use even e to the minus length of x, even the Euclidean length of x. That doesn't split, right? It's not the product of one-dimensional integrals. So I needed both symmetry, that's only dependent on r, plus the splitting. So Gaussian is used in many contexts because of these properties, right? It's the only thing that has all these properties. Oh, I forgot. I was reminded that I should repeat the questions from the audience because they can't record it, so I have to repeat them next time. I'll remember that. So we saw that. We saw that. Radial symmetry is crucial, as well as the splitting, which I didn't write down. I should do that. And then this is a question I already went through. Is the surface area of any d-dimensional object d times its volume? Picture proof of the same argument. That is a picture proof. As for spheres, works for anything. So the picture proof seems to work. Is this picture correct, right? We went through that already. And we did get, though, this quantity that's nice to know. This is true. You should check all these things for small dimensional spheres and so on, just as a sanity check. So now we'll prove that the volume is near the equator. So we're going to prove several of these things. So this will be by integration. There's no Gaussian trick here, but it'll be by integration. We will come back to using Gaussians for more things a little later. So we want to prove that most of the volume, say 99% of the volume of the D sphere is in the equatorial region. And the equatorial region is the absolute value of x1, so above and below the equatorial plane, right, is less than or equal to delta. So the first intuitive question I'm going to ask is what delta should be, and then we'll try to prove it, right? So here's a nice thing to this is something that you all know, but this is very central to this course, so I want to remark on this, right? That first question is the same as a question that I can rephrase in terms of probabilities, right? I want to know the 99th percentile of the absolute value of x1 when x is picked uniformly at random. We'll use this phrase a lot, so I'm going to abbreviate it UAR, uniformly at random, from the hypersphere. Okay? So again, this is extremely intuitively simple, right? But just think of that. So volumes and probabilities are related. After all, probability is just an integral of probability density, and volume is also an integral. So you expect the relation, but this is what we're asking. Okay. So more intuition of what delta should be. So here's more intuition, right? So the length of x squared is just Pythagoras, right? Sum of the coordinates squared. We know that the expected value of the length of x squared is at most 1. In fact, length of x is at most 1 in the sphere. Not only is at most 1, we actually know that it's approximately 1, right? So how close is it to 1? Do you know the answer? What's the expected value of x squared? From what we have already seen, what is it? What can you put here that's true? 1 minus 1 over d, right? Because we saw that most of the volume, I mean, it's not completely a proof. You have to sit and work it out. But that probability was falling exponentially, so you should be able to integrate to get 1 minus 1 over d. Okay. So in fact, expected value of x squared is 1 minus c over d for a particular constant c. You can work that out. Okay. By symmetry, all the expected value of x1 squared must all be equal, so each of them is 1 over d. So that suggests that delta, which is absolute value of x1 without the square, could be order 1 over root d, but we want that to hold with high probability. That's only expectation, right? So these were expectations. It doesn't imply high probability automatically. That tells you an intuition. By the way, even though let's go through this. For a general random variable, let's consider x1 absolute value to be a general random variable. It has second moment at most 1 over d. We saw that. That's this stuff. Okay. Does that automatically imply that with high probability means exponentially small failure probability, it's 1 over root d, order 1 over root d. That's not true, right? General random variables can have terrible tails. So if you had a polynomial density, the tail is so long that this won't be true. But for all the geometric quantities we are going to see, the tail will not be bad. It'll be exponential. So we already saw 2 exponential bounds. One is for the volume near the surface, volume away from the surface was exponentially small. Another one was the equator. So things work with very high probability. So in fact, even though this is not rigorously correct, it'll be true. Okay. By the way, one quick aside as a recap, I would like to prove, and we'll prove this, with high probability x1 is 1 over root d. We do know the expected value of x1 squared is at most 1 over d. Can you at least say this? The expected value of the absolute value is at most 1 over root d. Do we know this to be implied from what we know already? Anybody remember an inequality that might give you this? Cauchy-Schwarz. Yeah, Jensen's inequality is called, but proved by Cauchy-Schwarz. So for any random variable x, the expected value of the absolute value of x is less than or equal to the expected value of x squared. Oh, square root. And you prove it by Cauchy. This is Jensen's inequality, right? You prove it by taking square roots. Or just by convexity of the square function, or any number of ways, but that's true. So we do know that, but I want to tell you that, in fact, even though it's a fallacious argument to say expectation implies with high probability it's order that, it's true for geometric quantities, right? So they are fairly concentrated. So we'll do a proper proof by integration. So I should draw a picture on the board, so I'll erase this. So I'm going to find the volume of the following set. What is the set? A is the set of y so that x1 is greater than or equal to. This is all A. Both top and bottom. In that case, I made a mistake. There's a factor of 2 missing, sorry. So what I have here is only the top part, and it should be d minus 1 there, excuse me. So it should be c over d minus 1. So in the picture, I'll indicate all this. So this is c over root d minus 1 minus c over root d minus 1. I'm integrating this. I'm taking slabs and integrating, so this is a slab. And this is x1. This is dx1. And the volume of this slab, what is it? So this is radius 1. So little geometry here. This is radius 1. This is just basically planar because all dimensions are symmetric. And this is x1. So this is square root of 1 minus x1 squared. Okay. Now, I'm going to take the d minus 1 dimensional volume of this. Okay. This is a sphere of radius, so this flat thing, I guess I should have drawn this picture, is a sphere in d minus 1 dimensions of radius root 1 minus x1 squared. Right? And therefore, its volume is, I'm sorry. Therefore, that's the volume, right? So, yeah, the question is whether it shouldn't be multiplied by 2. The answer is yes, I made a mistake and didn't put the 2 there because I need this is only computing the top section, right? So I will correct that slide. Yeah, you have to have a 2 there. Good. Okay. So I get it's d minus 1 dimensional sphere of radius 1 has this volume, v of d minus 1. But now it has radius square root of 1 minus x1 squared, so you get that extra factor, and times dx1. Okay, so is this correct? Am I being careful about the point I made, right? Yes, dx1 is perpendicular to this, right? So that's fine. Okay, okay, so here's a nice standard trick. I mean, I'm going to tell you some of these tricks. They're just integration tricks, but then we use them quite often. So for the Gaussian integrals, these are tails. So when you want to compute the tail probability of a Gaussian, right, the probability that x is many standard deviations away, this is what you have to do. This is the integral. So you get x minus alpha, x over alpha. X is greater than alpha in this. This is alpha, by the way, to infinity. So x is greater than alpha, so I can throw that. And this is nice because this is integrable, right? E to the minus x squared, the derivative has an x in it. So you can integrate that. So that's how you often compute the tail probabilities of Gaussians. So that's a very good estimate if you go more than a few standard deviations away. Okay, so I have to integrate that. Sorry, I have to integrate that, and I throw in this extra factor, this x over alpha factor here, right? And I want to claim that is that. It needs only to be checked, but basically Vd minus 1 comes out. That's C. And, you can check that. You can check that there's no mistake there. Yeah? Was there a question? No. I think I made no mistakes, but it's worth checking to make sure. In the book, these are written down. Most steps are written down so that you can check. Okay. And now I want I want a denominator. So I wanted the ratio of the volume of A to V of D. Now we've got volume of A in terms of V of D minus 1. And my object now is to get V of D in terms of V of D minus 1. Okay. Roughly, V of D is V of D minus 1 over square root of D. Because we lose as square, the volume is D to the D over 2 in the denominator, so you lose the square root of D each time. So that's what roughly is true, but we'll prove that. So, I'm sorry. So here's the proof. Volume of the hypersphere, that's V of D, is at least the volume of the cylinder of this height contained in there. So it's the volume of this kind of cylinder. So I'm going to take that volume as a lower bound on the volume of the whole thing. Okay. Again, there are a few more steps in the notes. If you don't agree with something, you can ask me. So, which is, now why is that? Okay, let's see if you agree with that. So this is supposed to be the volume of the cylinder whose height is 2 divided by root D minus 1. So it's 1 divided by root D minus 1 away from the equatorial plane. So why do you get this factor? Why do you get that? Right? Roughly, what is this factor coming from? From the fact that this thing has radius 1 minus x squared square root, and then this height is this 2 over root D minus 1. So I think that's all also done correctly, worth checking. But so at the end of it, you get a theorem which says that for any constant c greater than 1, c is anything greater than 1, more than d dimensions, more than 3 dimensions, you have that at most this fraction of the volume of the sphere has x1 greater than this amount. So again, I expect the absolute value of x1 to be roughly 1 over root d, sorry. I put down 1 over root d minus 1 here, which is about the same. D is large. So the probability that is greater than that falls off exponentially with c. Okay. All of these things will be exponential falls. Tails will be very well behaved. Okay. Again, please do check all the details. So I guess the question is, why did we recompute V of D in step 6? That's because I wanted the denominator and the numerator to be in terms of V of D minus 1. So that's not a very interesting question. Now this result implies a bunch of things. It's another way to prove, so the equator being heavy is another way to prove that the volume of the whole sphere goes to 0, and that requires another picture. So I'll draw a fresh sphere. Let's draw a big one here. So we proved that if I put here c times root log d, in the last slide I had only a c, now I'm putting a c times root log d. I had a root d minus 1, but almost the same as root d. Okay. Then the volume was e to the minus this squared. So I put the root log d so that I get e to the minus this volume. I'll get e to the minus c log d, because I squared it, times the volume of the sphere, which with large enough c is less than 1 over d squared. C is at least 2, let's say. It's at least 1 over d squared. Okay. That's for the x1 axis. And I could do the same thing for the x2 axis. This is x2. And I know, okay, so let me, this shaded region is small. But from the x2 picture, I also know that this shaded region is small. Okay. Now, if I take out those two shaded regions in 2 dimensions, in d dimensions, I have to take out d of them. What's left is a cube. You have to convince yourself, but what is left is a cube, right? I mean, so let's, I think that's the next statement. Okay, yeah, it doesn't say precisely, but so, yeah, so it does say here. So it's 1 over d squared, each of those things I take out. And I have to take out d of them, 1 for each axis. So once I take them all out, I've still only taken out 1 over d of the volume. Okay. So, for example, half the volume is still left, but that's all inside the cube. Now, the cube has a much smaller side than the radius of the sphere, because the cube has only side about root log d over root d. Again, d is going to infinity, so this is going to 0. So it's a tiny cube, right? So what this is saying is that a tiny cube in the center of the sphere contains half the volume or more. Okay? Again, another, not a surprise anymore, because we've seen many of these things. And the cube's volume is the side raised to the power d, so that goes to 0, right? Now, the volume of the sphere we saw more exactly did not have this log factor, right? It still had this factor, that is correct. That's a higher order term, that's correct. But it didn't have the log factor. This is a crude argument which leaves the log factor in. Okay. But that's still going to 0 because log d is much smaller than d. So that's another proof. I mean, you can give multiple proofs that this goes to 0. Okay, so yeah, I mean that you mean this thing, the d minus 1 dimensional surface. Yeah, the bulk of the volume is near the d minus 1 dimensional surface, which is the equatorial plane. That, right? That answer. So maybe we should revisit that symmetry question, which I meant to, which is, remember we had this puzzle last time, from maybe you asked the question too, right? That so anything can be the North Pole. I don't care. It's not fixed. So for every North Pole, so this region has 99% of the volume. So does this region, right? And so on. So how do we reconcile that? Okay, even we didn't quite answer that question. That's what revisiting. So why is that not contradictory? Right. So if you intersect, so if it's 99%, if you intersect 10 of them, the intersection will have only 90% perhaps, right? So if you intersect a huge number of them, the intersection could be very small. Still will contain the origin, but it will be very small. So that's not a contradiction. The other little thing was that equator and the surface. So everything was near the surface, everything was near the equator. So these things are very heavy. These things together contain 99% or 98% of the volume of the sphere. Okay? It doesn't look at all possible in 3D or 2D, but it's true. because we did say it's all near the surface and it's all in equatorial plane. So that's true. Okay. So another consequence of the equator thing is that is a general principle in some sense. If I pick two independent random vectors uv, and so I'm writing here the expectation of a vector. What I mean is component-wise you take expectations, right? Usually you take expectations of real valued random variables. So each component you take the expectation, and they're zero vectors. So each component of u and v have expectation 0, and they're independent. Then with high probability, it's another phrase we'll use a lot, so I'll use WHP for with high probability. Usually it means exponentially small probability of failure, right? These vectors u and v will be nearly orthogonal. V will not have a component, very much of a component along u. Okay, we'll make it we'll quantify that. So intuitively this is clear, but dot products measure correlation, and this says that independent vectors will not be correlated, right? So intuitively that should be the case, and in fact it is the case, right? So we'll prove that using the equator thing. We'll prove something stronger. So the way to see that for two vectors, and I'm going to do it for multiple vectors in a minute. For two vectors, if u and v are independent, uniform at random from the unit sphere, we'll see that their dot product is very small compared to the lengths. First, the length is big, right? With high probability, the length of length of u is this big. So that's clear, right? Why is that? I mean, what result implies that? Just a sanity check. Volume near the surface implies that. So yeah, so that implies that. So first we pick u, and then I'm going to rotate the coordinate system so that u is the north pole. I'm allowed to do that. I can choose any north pole. So then u becomes this vector with only the first component, zeros in the other components. Now I pick v. Now v is independent of u, so the rotation does not affect how v looks, right? That's just a change of coordinate system. It doesn't affect how v looks like. And we saw from the equator result that with high probability, the absolute value of v1 is order 1 over root d. And now I take the dot product. I only have to worry about v1, and so the cosine theta, which is the dot product divided by the length, is something like this. 1 over root d times the length of u is that. That's roughly then there are higher order terms, but it's roughly 1 over root d. And that implies theta is almost 90 degrees. Okay, cosine inverse is that. Okay, that's for two vectors. What happens if I pick n vectors? If I pick n vectors IID in d-dimensional space, one can prove first all of them lie near the surface if log n is much smaller than d, and secondly all the dot products are small. Again, this is a log. If log n is not very big compared to d, that's n is smaller than 2 to the d, then the dot products also go to 0. Okay. So let me not actually prove this. I don't know, maybe I'll ask questions about, so how do we prove the first one? I want to say that with high probability, all the xi are big. And I want to get the log factor. First, where would I get that the first one, x1 is big in length? That we saw. That's from the volume near the surface. How would I get that all of them are near the surface? Union bound, right? So because the probability that one of them, the answer was union. So the probability that one of them is not near the surface, whatever it is, and then you have to multiply it by n, right? But the failure probability is exponential, so you get a log. This is a calculation that you can do at home. Okay. How about this? xi dot xj. So we proved for one pair uv, we get u dot v small. I mean, we did some rotation of coordinates and so on, but those ought to be ignored. It's all independent of the coordinate system. Okay. So how do we get this? Same union bound, right? because there are n squared of them now. Maybe I should do that, but there are n squared of them. So if P is the probability of failure of one of them, probability that x1 dot x2 is greater than or equal to that quantity, 6 root log n over root t minus 1, then I want n squared times p. Now this probability I know is less than or equal to e to the minus, I forgot whether it's c squared or c. That's the equator thing is c squared, right? So yeah, so it's the square of this, basically. It's log n times some constant. I think 10, I'll put 10 there. 6 squared divided by 2. I mean, you have to go back to the actual proof. So this is less than or equal to 1 over n to the 10. Now, the n squared, we have to union n squared events, not n events, but the n squared only costs you a factor of 2 more because we're taking logs. That's the point, right? Again, please work that out. That's just a union bound that gets you that. So even if I pick a lot of vectors, they're all fairly mutually orthogonal. So I want to do one more thing, and then we can stop. So how do you pick uniform random points? Actual, algorithmically, how do you sample points from a unit ball? So in 2 and 3D, the algorithm, the simplest algorithm to do that is the following. So I want to pick a uniform random point from this circle. That's a bit difficult because the coordinates are dependent, right? Because we have this constraint, x1 squared plus x2 squared less than or equal to 1. So the coordinates are not independent. So you put it in a box of side 2. And I pick random points from the box. Now I can do that because x1 and x2 are independent. And I accept the point only if it's inside the sphere. Okay? This is called rejection sampling, right? In statistics, the rejection sampling is just saying the following. I want to sample from a distribution which is somewhat hard, which is uniform distribution of the sphere, P of x in this case. I instead draw a sample from an easier distribution, Q of x, which is uniform in the cube because they're independent, and then accept with this probability. It's easy to check that the samples I get are correct, IID samples with distribution P of x. Okay. Here is a profound question. Would you do the same procedure if I've told you to pick from a 1,000-dimensional sphere uniform random point? Would you do the same procedure in a 1,000-dimensional sphere? No. The answer is he's shaking his head, but he didn't. No. Why wouldn't you do it? Yes. So the answer is yes. The volume of the sphere is exponentially smaller, so you'll reject most of the time. So the cube is so much bigger than the sphere that this would make rejection very likely. Okay. So in fact, this is a general phenomenon which we won't do in this course, but if you see one of the later chapters of our book on Markov chains, it turns out to be interesting to pick random uniform points from general sets, let's say convex sets, simplices, cubes, spheres, polytopes in very high dimensions. And rejection sampling does not work for this very reason, because the enclosing object is always much bigger. Okay? So what do you do if it doesn't work? You can look up that chapter, or I can give you literature. We won't actually do that in this course. You employ a Markov chain Monte Carlo method, but so you wouldn't do this in 1,000 dimensions. Here's a procedure that does work for spheres. It doesn't work for general objects, and that's much more complicated. For spheres, the correct procedure is we pick x1 through x3 independent from standard Gaussian. This is mean 0, variance 1, normal density. Now you normalize the length to 1. That's a uniform random point of length 1 from the surface of the sphere. But we want to pick from inside. So I'm going to scale it by a factor rho and take that as my sample. So again, I have a sphere. I picked a Gaussian point x with Gaussian density over all of space, and then I scaled it down to x over length of x. Then I'm going to scale it down to one of these points. This is rho times that. But I have to pick rho with the correct density. Rho is a real random variable. I have to pick it with the correct density, right? What is the density of rho? Uniform is not right? It's not uniform over 0, 1. Yeah. So which is? It's not uniform, but yeah, it's got to be the area. But what might it be? So you have to look again at the differential element, right? So I want that volume. And that volume should be a function of rho to the d minus 1. So rho, probability that rho is equal to x is proportional to x to the d minus 1 between 0 and 1. I mean, divided by the integral, which is v, but you have to normalize it. But so you have to pick rho with the correct density, and then you get a point uniformly at random from the sphere. Big question, not such a big question. So I think, yes. The question is, instead of picking according to the normal, what if I pick x1 to x3 independent minus r to plus r uniform, right? So what is wrong? That doesn't work. Why not? Okay, so we should draw a picture. I think that's one of the homework problems, but anyway, in the back of the book. So what the suggestion was this, right? So here's a sphere from which I want to pick points. I pick a point uniformly at random from the cube, and then scale it down to length 1. So I pick it somewhere here, let's say, and then scale it down to this point. So will that be correct? No. So yes, the answer is no, but why won't it be correct? Some directions have more points. Which direction has more points? The corner, right? Because the cone here is very, very long, so this volume is much bigger than this volume, right? So that doesn't work. So you need a radially symmetric density in any case, but any radially symmetric density will do. Okay? So if I pick points with probability e to the minus, so Gaussian is e to the minus r squared, I could instead do e to the minus r. That's fine. But it has to be radially symmetric. Okay, so we'll go today. The next time I'm going to do the following. We are going to prove an annulus theorem for Gaussians, that if I pick a Gaussian, it's also true that there's a small annulus where points lie. And to do that, we'll need a concentration result, which is actually quite general. So it's saying that sums of independent random variables are concentrated, which we'll prove, and that'll imply Chernoff and all kinds of bounds.